Welcome to For Science Salah Lotfy channel, where science meets curiosity. في هذه القناة لا نكتفي بعرض الأبحاث العلمية، بل نترجمها إلى المعرفة التي تصل إليك أينما كنت. Our mission is to make global scientific research understandable, accessible, and multilingual. جميع الفيديوهات العلمية هنا مترجمة إلى اللغة العربية، بالإضافة إلى لغات عالمية أخرى. French, Spanish, German, Urdu, and more. Because science speaks every language. نعم، العلم يتحدث بكل اللغات، ونحن نحرص أن يصلك بلغتك. If you're passionate about science, you're in the right place. اشترك الآن وابدأ رحلتك مع العلم خطوة بخطوة. For Science Salah Lotfy channel, العلم للجميع.
Welcome to For Science Salah Lotfy channel. Today we explore a fascinating piece of research from Cairo University that integrates chemistry, nanotechnology, biology, and electronics into one breakthrough. The study focuses on a nano Schiff-based copper complex, a material that has shown remarkable multifunctional properties. Why is this important? Because in the growing field of bioelectronics, we need materials that are not only conductive and flexible, but also biologically safe and even protective against infections. This nano Schiff-based copper complex aims to combine electrical, mechanical, and biological functions in one material. Structurally, the complex is nanostructured, with particles about 33 nanometers in size, a high surface area, and a porous texture. This increases its solubility, its reactivity, and even its ability to release therapeutic agents over time. Mechanically, it shows a rare auxetic behavior. It expands laterally when stretched. This property makes it ideal for flexible electronics, wearable sensors, and implantable devices that must move with the body. Thermally, the material undergoes a phase transition near 44 degrees Celsius, switching from insulator to conductor. This unique property allows for temperature-triggered sensing and even controlled drug release. Biologically, the copper complex is highly active. It produced a 30mm inhibition zone against Bacillus subtilis. It also showed significant anti-cancer potential against breast cancer cells, with an IC50 value of only 18.4 micrograms per milliliter. What makes this study outstanding is its integrated approach. Instead of looking at electrical, mechanical, or biological properties separately, the researchers analyzed them together. They created a complete profile of how this material behaves, a full performance map. This means the material can act as an electronic element and as a bioprotective therapeutic layer inside the body. So where can this technology lead us? Medical implants that resist microbial contamination while maintaining stable electronic signals? Wearable healthcare devices that are flexible, durable, and biocompatible? Smart wound dressings that combine infection control with electronic monitoring? And potentially, new anti-cancer therapeutic systems that merge diagnostics with treatment. Economically, these multifunctional materials could lower healthcare costs and open new markets in bioelectronics. This is For Science Salah Lotfy channel, bringing you knowledge from the lab to the screen. Stay tuned. Welcome to For Science Salah Lotfy channel. In today's episode, we are highlighting an outstanding scientific contribution that merges nanoscience, chemistry, and physics into the exciting world of bioelectronics. The research we present is titled, Integrated Analysis of Nano Schiff-Based Complex for Bioelectronic Applications. This work was published in the internationally renowned journal Scientific Reports under Springer Nature. The article appears in Volume 15, Article number 31202, 2025. The paper was received on the 25th of March 2025, accepted on the 18th of August 2025, officially published online on the 25th of August 2025. Such publication details reflect the careful review process and the significance of this contribution to the scientific community. Let us now acknowledge the distinguished team of researchers behind this work. We will list each contributor and affiliation. Dr. Emad Mousa, Physics Department, Faculty of Science, Cairo University, Giza, Egypt. For further contact, his email is listed as emad@sci.q.edu.eg. Dr. Ahmed Tammam, Physics Department, Faculty of Science, Cairo University, Giza, Egypt. Dr. Ahmed Refaat, Chemistry Department, Faculty of Science, Cairo University, Giza, Egypt. Professor Dr. Gehad Mohamed, Chemistry Department, Faculty of Science, Cairo University, Giza, Egypt, and additionally affiliated with the Nanoscience Department, Basic and Applied Sciences Institute, Egypt, Japan University of Science and Technology, New Borg El Arab, Alexandria, Egypt. This combination of expertise across physics, chemistry, and nanoscience reflects the interdisciplinary strength necessary for pioneering research in bioelectronics. Now, the focus of the paper, The focus of the paper is on the Nano-Schiff base complex, a promising material investigated for its potential in bioelectronic applications. Through integrated analysis, the researchers explore its structural, electrical, and biological characteristics, aiming to open pathways for advanced diagnostic tools, flexible medical devices, and smart therapeutic systems. Advanced diagnostic tools, flexible medical devices, smart therapeutic systems. The study combines advanced experimental techniques with nanostructural insights, positioning this complex as a material with both scientific novelty and technological impact. This research opens pathways that could enable new diagnostics and implantable or wearable bioelectronic systems. This remarkable achievement is a clear example of how Egyptian researchers are contributing to global scientific progress through innovative ideas and rigorous experimentation. Stay tuned as we continue exploring the fascinating details and implications of this research in the upcoming segments. And as always, thank you for following For Science Salah Lotfy channel. Welcome to For Science Salah Lotfy channel. Today, a copper-2 Schiff base complex that blends nanotech, electronics, and biology. So, what exactly are these remarkable compounds? At their core, Schiff bases are organic molecules that form powerful complexes when they bind to a central metal ion. This unique structure is a powerhouse of biological activity. The specific shape and electronic properties of the complex allow it to interfere with harmful biological processes. This is why they exhibit such a broad range of activities, from being potent antioxidant, antibacterial, and antifungal agents, to showing promise as antiviral and even anti-cancer therapies. Their ability to target specific biological functions makes them a hot topic in medicinal chemistry. Beyond medicine, these same structural features make them stars in material science. Their electron-rich nature gives them fascinating electronic properties, making them useful as semiconductors in devices like highly sensitive sensors and next-generation solar cells. But here's the real magic. Their properties are tunable. By simply swapping the central metal ion or by tweaking the organic ligand, scientists can precisely control the complex's conductivity, color, and performance. This molecular-level engineering is vital for creating custom materials for specific tasks, from preventing corrosion to stabilizing plastics. The study focuses on a copper-2 complex based on a Schiff-base ligand. The ligand derives from 2-hydroxy-1-naphthaldehyde and 1,8-diaminonaphthalene. Researchers tested its electronic, biological, and mechanical behavior together, an integrated approach. We start with X-ray diffraction, or XRD, to probe the material's atomic structure. This reveals whether atoms are arranged in an orderly crystalline lattice or a disordered amorphous state. High-resolution transmission electron microscopy, or HRTEM, gives us a nanoscale view, allowing us to measure individual particle sizes and directly visualize the internal atomic lattice. Field emission scanning electron microscopy, FESM, maps the surface. It generates detailed 3D-like images of particle shapes and how they cluster, revealing the material's overall morphology. With atomic force microscopy, or AFM, a tiny probe scans the sample to create a 3D topographic map that precisely measures surface roughness down to the nanometer scale. To measure porosity, nitrogen adsorption analysis, or BET, determines the specific surface area and pore size by measuring how much gas adheres to the material's surface. The ultrasonic pulse echo technique helps us understand its mechanical properties. By sending sound waves through it, we can determine its acoustic impedance and overall rigidity non-destructively. Thermogravimetric analysis, or TGA, tests how the material behaves when heated. By tracking its weight as temperature rises, we can pinpoint its decomposition point and thermal stability. Differential scanning calorimetry, or DSC, complements this by measuring heat flow. It helps us detect phase transitions like melting and quantifies the energy involved in these changes. We also test its electrical properties using impedance spectroscopy. This measures how conductivity changes across different temperatures, which is crucial for potential electronic applications. Finally, we assess its biomedical potential with biological assays. This includes testing its ability to inhibit microbial growth and evaluating its cytotoxicity against cancer cells. First, let's look at its structure. Under the microscope, the material reveals a complex nanoscale morphology. Think of it like a sponge, but on a scale 1,000 times smaller than a human hair. This structure creates an incredibly high surface area and intricate network of pores. This isn't just for show. This porosity is key to its enhanced bioactivity, creating countless docking sites for interactions with cells and biological molecules. Mechanically, the material exhibits a fascinating and rare property known as auxetic behavior. When you stretch most materials, like a rubber band, they get thinner in the middle. But this material does the opposite. When stretched, it actually expands sideways. This counterintuitive property is incredibly useful for applications that need to conform to complex dynamic surfaces, like a smart bandage that moves and flexes with your skin without peeling away or losing contact. Electrically, it's a powerhouse in wet environments. The material boasts high ionic conductivity, meaning it allows charged ions to flow through it easily when hydrated. This is crucial for interfacing with biological systems, which run on ionic currents. This property also fuels its antimicrobial power. The flow of ions can physically disrupt the outer membranes of bacteria and other microbes, essentially punching holes in their defenses and causing them to break down. The material also has a built-in thermal switch. At normal body temperature, it acts as an electrical insulator. But when heated to around 44 degrees Celsius, it undergoes a phase transition and becomes a conductor. This specific temperature is significant. It's just above fever-grade temperatures, suggesting the material could be designed to activate only in areas of inflammation, infection, or even at the site of a tumor being treated with hyperthermia. These properties translate into powerful biological results. When tested against Bacillus subtilis, a common bacterium, the material demonstrated potent antimicrobial activity. It created a massive 30mm zone of inhibition, a clear, circular area on the petri dish where no bacteria could survive. This result is a dramatic visual confirmation of its ability to effectively kill microbes on contact, making it a strong candidate for advanced wound dressings. Beyond bacteria, the material also showed strong anti-cancer effects. In lab tests against MCF7 breast cancer cells, it achieved an IC50 value of just 18.4 micrograms per milliliter. The IC50 is the concentration required to stop 50% of the cancer cells from growing. To achieve this with such a small amount of material highlights its high potency and potential for targeted cancer therapy applications. So what does this all mean? When you combine its unique porous structure, its flexible auxetic mechanics, its switchable conductivity, and its potent antimicrobial and anti-cancer activity, you don't just have one interesting material. You have a truly multifunctional platform. These results pave the way for a new generation of adaptive bioelectronic devices that can sense, respond, and treat in complex biological environments. Applications include implantable bioelectronic devices where infection control is crucial, wearable healthcare electronics that demand flexibility and durability, smart wound dressings, integrating antimicrobial protection with electronic monitoring, therapeutic systems combining diagnostics with targeted treatment. This work moves bioelectronics toward integrated multifunctional materials that merge biology and electronics. Thanks for watching. Subscribe to For Science Salah Lotfy channel for more breakthroughs in science and technology. Welcome to For Science Salah Lotfy channel. Today we follow the experimental path behind a Schiff-based copper complex with bioelectronic and biological potential. We will cover synthesis, instrumentation, results, and why this material matters. Key reagents: 1,8-diaminonaphthalene, 2-hydroxy-1-naphthaldehyde, and copper chloride dihydrate, the metal source. Ethanol, DMF, and diethyl ether were used, all analytical grade to ensure reproducibility. High-purity reagents avoid side products and give clean characterization data. Synthesis follows a two-step route: ligand formation, then complexation with copper. Let's look at how each step was performed. Our journey begins with the synthesis of a specialized organic molecule known as a Schiff-based ligand. These compounds are prized for their ability to tightly bind to metal ions, forming stable complexes. To create our ligand, we start with two key building blocks: 1,8-diaminonaphthalene, a rigid molecule with two amine groups, and 2-hydroxy-1-naphthaldehyde, which provides the reactive aldehyde and a crucial hydroxyl group for chelation. The synthesis is a classic condensation reaction, where these two components are combined in hot ethanol. The mixture is heated under reflux, a process where solvent vapors are continuously cooled and returned to the flask, allowing the reaction to proceed at a constant, elevated temperature without boiling away. After 3 hours of reflux, the reaction is complete, signaled by the formation of a deep violet precipitate. This solid is our desired Schiff-based ligand. Now, we must isolate and purify it. The mixture is cooled, and the product is collected by filtration through a Buchner funnel. It's then washed thoroughly with cold ethanol to remove any unreacted starting materials or soluble byproducts. Finally, the purified ligand is dried under a vacuum to completely remove any residual solvent, yielding a fine, stable powder, ready for the next stage. With our ligand prepared, the next step is to introduce the metal center. This is where coordination chemistry comes into play. We chose copper-2 for its fascinating electronic properties and its known biological activity. The purified ligand is first dissolved in a small amount of dimethylformamide, or DMF, a solvent capable of dissolving the large organic molecule. This solution is then carefully added to a solution of copper-2 chloride in hot ethanol. Almost immediately upon mixing, a new solid begins to precipitate as the ligand wraps around the copper ion, forming the target complex. The mixture is refluxed again to ensure the complexation is complete and to promote the growth of a well-defined solid. The resulting dark precipitate is the crude copper complex. Its purification follows a similar path. It's filtered and then washed, this time with diethyl ether, to remove any remaining organic impurities. To achieve the highest purity, the complex is recrystallized. This involves dissolving it in a minimum amount of hot ethanol and allowing it to cool slowly. As it cools, the solubility decreases, and the complex crystallizes out, leaving impurities behind in the solution. After a final filtration and drying, we are left with our final product, a beautiful, microcrystalline solid of the Schiff-based copper-2 complex. Synthesizing a new compound is only half the battle. Now we must rigorously prove its identity and structure through a suite of analytical techniques. This characterization process is like chemical detective work, where each test provides a crucial clue. We began with the most fundamental test, elemental analysis. This technique precisely measures the percentage of carbon, hydrogen, and nitrogen in the sample. Our results confirm that the elemental composition matched the theoretical values calculated for our proposed copper complex structure, providing the first piece of evidence that our synthesis was successful. Next, we used Fourier transform infrared or FTIR spectroscopy to identify the chemical bonds present. This technique shines infrared light on the sample and measures which frequencies are absorbed by the molecule's bonds as they vibrate. The resulting spectrum is a molecular fingerprint. Crucially, we saw the disappearance of the amine and aldehyde peaks from our starting materials and the appearance of a strong new peak corresponding to the imine bond, confirming the formation of the Schiff base. We also observed a shift in the hydroxyl group's frequency, indicating it had bonded to the copper ion. To get a more detailed picture of the ligand structure, we turned to nuclear magnetic resonance, or NMR, spectroscopy. While the paramagnetic nature of the copper-2 ion complicates the NMR spectrum of the final complex, the spectrum of the ligand itself was incredibly informative. It provided a complete map of the proton environment, confirming the precise connectivity of the atoms and showing that the condensation reaction had occurred exactly as planned, giving us confidence in the organic framework of our complex. Ultraviolet visible spectroscopy, or UV-Vis, allowed us to probe the electronic properties of our new molecule. The spectrum of the complex showed intense absorptions in the UV region, which are attributed to electron transitions within the aromatic system of the ligand. More importantly, new, broader absorption bands appeared in the visible region. These are the characteristic DD transitions of the copper-2 ion within the ligand field, and they are responsible for the complex's deep color. The position and intensity of these bands give us valuable information about the geometry around the metal center. To get the definitive confirmation of our compound's identity, we used mass spectrometry. This powerful technique weighs individual molecules with incredible precision. The mass spectrum showed a clear peak corresponding to the exact molecular weight of our target copper complex. This result provided unambiguous proof that our ligand had indeed coordinated with a single copper ion, verifying the overall structure and stoichiometry of the molecule we worked so hard to create. With the molecular structure confirmed, we next investigated how these molecules pack together in the solid state using X-ray diffraction, or XRD. By analyzing the pattern of diffracted X-rays, we determined that the complex crystallizes in a triclinic system, the least symmetrical of the 7 crystal systems. The analysis also gave us a crystallinity index of approximately 67%. This tells us that while the material is largely ordered and crystalline, about a third of it exists in a more disordered or amorphous state. To visualize the material surface, we used field emission scanning electron microscopy, or FESM. The high-resolution images revealed a surface composed of non-uniform, irregularly shaped grains that were clumped together in agglomerations. This observation of a polycrystalline morphology, meaning it's made of many small crystalline domains, is perfectly consistent with the data we obtained from XRD. Finally, we used high-resolution transmission electron microscopy, or HRTEM, to look even closer, imaging the individual nanoparticles themselves. These measurements gave us an average particle size of about 33.7 nanometers. Interestingly, this was larger than the average crystallite size of 25.6 nanometers calculated from our XRD data. This discrepancy is highly significant. It suggests that each individual particle we see in the microscope is not a single perfect crystal, but is instead composed of smaller crystalline domains, or crystallites embedded within a surrounding shell of the amorphous material we detected earlier. This detailed structural understanding is critical for interpreting the material's properties. To understand its physical behavior, we probed its mechanical properties using ultrasonic pulse echo. This technique sends a high-frequency sound wave into the material and analyzes the returning echo. By measuring the echo's travel time and energy loss, we calculate fundamental characteristics like stiffness and density, which are critical for determining how the material responds to physical stress. From this, we calculated an acoustic impedance of 13.4 megarails. This value, much higher than human tissue, indicates a dense structure that efficiently transmits acoustic energy. This combination of rigidity and, as we'll see, flexibility is a highly unusual and desirable pairing for advanced bioelectronic interfaces. But the most remarkable discovery was its negative Poisson's ratio. When stretched, our complex becomes thicker, a counterintuitive property known as an auxetic response. This is incredibly valuable for flexible implants. An auxetic material can conform to the body's moving surfaces, bending and stretching without losing contact or integrity, making it tougher and more resilient. Next, we investigated its thermal stability using TGA and DSC. TGA measures mass changes with temperature, showing how the material breaks down. Simultaneously, DSC measures heat flow, revealing subtle phase transitions that don't involve mass loss, like changes in crystal structure. The TGA results showed a clear decomposition pathway. Minor water loss occurred around 70 degrees Celsius, followed by the primary breakdown of the organic ligand between 250 and 450 degrees. By 1000 degrees, all that remained was a stable residue of copper to oxide, confirming the material's composition and its upper thermal limit. The DSC data, however, revealed something far more exciting at a much lower temperature, a distinct endothermic peak, right around 44 degrees Celsius. This meant the material was absorbing energy to fuel a solid-state phase transition. Its proximity to human body temperature strongly suggested this could be exploited for biomedical applications, hinting at a smart, responsive behavior. To confirm this and characterize its electronic nature, we measured its AC conductivity with a precision LCR bridge. This technique probes how the material responds to an alternating electric field across a vast frequency spectrum, from 50 Hz to 5 MHz, giving us deep insight into its charge transport mechanisms. The results showed that conductivity increased with frequency, following Yoncher's power law. This behavior is the hallmark of charge transport in disordered semiconductors, confirming that electrons move by hopping between localized sites within the molecular structure rather than flowing freely as in a metal. Crucially, when we measured conductivity versus temperature, we saw exactly what the DSC data predicted. As the temperature crossed 44 degrees Celsius, the conductivity increased dramatically. This was definitive proof of an insulator-to-metal transition. Below this temperature, it's an insulator, above it a conductor. This switchable adaptive behavior is the key to its potential, enabling smart sensors that activate with a fever, or bioelectronic devices that modulate their function based on the body's thermal state. With the material's physical and chemical properties characterized, the crucial next step was exploring its biological activity. Could this complex do more than just conduct electricity and change shape? The investigation began in microbiology, using a classic technique, the Agar well diffusion assay. This method provides a clear visual answer to a simple question. Can our material stop harmful bacteria in their tracks? The results were striking. When tested against common pathogenic bacteria, the copper complex demonstrated significant power. On the agar plates, clear, bacteria-free halos, known as zones of inhibition, formed around the complex. The size of this zone is a direct measure of antimicrobial potency. This action is likely due to the copper ions within the complex, which disrupt bacterial cell membranes and interfere with essential enzymes. In an era of growing antibiotic resistance, discovering new materials with such strong antibacterial properties is of paramount importance. But the investigation didn't stop with bacteria. The team ventured into oncology, testing the material's effect on a well-established human breast cancer cell line, MCF7. In these cytotoxicity tests, the goal is to see if a compound can selectively kill cancer cells. The results were again highly promising. The Schiff-based copper complex exhibited notable anti-cancer activity, reducing the viability of the cancer cell population. This places it in the exciting class of metallodrugs, which use metal ions to fight diseases like cancer. This dual-action bioactivity opens up a world of therapeutic possibilities, especially when combined with the material's unique electronic and physical properties. This is where it becomes a cornerstone for next-generation biomedical devices. Imagine a smart wound dressing coated with this complex. Its conductivity could electrically monitor healing, while its antimicrobial nature prevents infections. Or consider an implantable device for targeted cancer therapy. The material could act as a reservoir, releasing its therapeutic payload on demand, triggered by a specific temperature change or an electrical signal. So let's step back and appreciate this symphony of properties. Its nanoscale porosity acts as a network of microscopic reservoirs, perfect for loading therapeutic molecules. Its remarkable auxetic mechanics mean that when stretched it gets thicker, not thinner, ensuring robust contact on flexible surfaces. Finally, its adaptive thermal and electrical behavior acts as a command and control system. Together, these traits bridge the gap between electronics and biology. The porosity enables drug delivery, the auxetic nature allows for stretchable devices, and the responsiveness provides the switch to trigger these functions. It's a conductor, an antimicrobial, and a sensor all in one. The journey of this material from concept to a synthesized, biologically active substance is a testament to the creativity of modern materials science. Its potential in smart healthcare, bio-integrated electronics, and targeted therapies is vast. We've only just begun to explore what's possible. Thank you for joining us. If you're fascinated by the future of materials that can sense, heal, and compute, be sure to subscribe to the For Science Salah Lotfy channel for more cutting-edge research. Welcome back to For Science Salah Lotfy channel. Today we explore groundbreaking research on a nano Schiff-based copper complex designed for bioelectronic applications. This material is not only structurally fascinating, but it also shows unique electrical, thermal, and biological properties, qualities that make it an exciting candidate for future biomedical and electronic devices. In this video we'll cover electrical behavior, antimicrobial and anti-cancer activity, structural features, and what it means for bioelectronics. Let's begin with the electrical conductivity across temperature phases. First, how conductivity changes with temperature. To understand this novel complex, researchers measured its AC conductivity across a wide temperature spectrum, from 291 to 391 Kelvin. They wanted to observe its dynamic response to thermal energy. As the temperature was carefully increased, a fascinating story unfolded, revealing not one but four entirely distinct electrical phases, each with its own unique properties and governing physics. These phases, labeled I, II, III, and IV, are not just arbitrary divisions, they are fundamentally different states, each with a unique charge transport mechanism. Let's delve into the physics of each phase to see what makes this material so special. We begin in phase 1, below 311 Kelvin. In this colder state, the material acts as a classic insulator, its electrons tightly bound. However, when probed with an alternating current, conductivity increases with frequency. This is a telltale sign of a quantum phenomenon. The data perfectly matched models for quantum mechanical tunneling, or QMT. This means that instead of having enough energy to go an energy barrier, electrons were passing it, a feat impossible in classical physics but allowed by the rules of the quantum world. As the temperature enters phase 2, between 313 and 321 Kelvin, something extraordinary happens. Right around 316 Kelvin, the material undergoes a sudden and profound transformation, a rare insulator-to-metal transition, or IMT. Its electrical resistance plummets, and it conducts electricity like a metal. The signature is unique. Conductivity first dips with frequency before skyrocketing upwards. This suggests a deep structural reorganization is taking place. The atomic arrangement shifts, creating pathways that liberate electrons, allowing them to flow freely. Witnessing this at a near-ambient temperature is exceptionally rare. Past the metallic phase from 323 to 343 Kelvin, the material enters phase 3 and settles into another conduction mode. The dominant mechanism is small polaron tunneling. A polaron is an electron coupled with a slight, localized distortion it creates in the surrounding crystal lattice. This electron plus distortion cloud becomes the charge carrier. In this phase, these polarons hop or tunnel from one available site in the lattice to the next in a step-by-step movement. Once again, the experimental data precisely fits the theoretical predictions. Finally, in phase 4, from 345 to 391 Kelvin, the conductivity becomes almost completely independent of temperature. Thermal analysis provides the answer. At these temperatures, the material releases volatile components, water and chlorine from its structure. Their departure permanently alters the lattice, creating stable defects. Conduction is now governed by correlated barrier hopping. In this model, one carrier hopping over its energy barrier influences the barriers of its neighbors, making it easier for them to hop too. It's a cooperative process dictated by the new structure. This journey through 4 electrical personalities in one material is a blueprint for innovation. The sharp, predictable switch at 316 Kelvin makes it perfect for highly sensitive thermal sensors. Imagine electronics that adapt on the fly, reconfiguring circuits in response to temperature. In the biomedical field, this could enable smart devices like a bandage that detects a fever and automatically administers medicine. This discovery opens a new frontier for designing intelligent, responsive materials for the next generation of technology. To understand the mechanism further, the team studied activation energy. At lower temperatures, activation energy was very high, up to 6.2 electron volts, indicating band-type conduction. At higher temperatures, the values dropped dramatically, reaching nearly zero at high frequencies, pointing to proton hopping conduction. This unusual transition near 316 K suggests structural reorganization, perhaps a planarization of the ligand scaffold, enhancing electron delocalization and metallic-like conductivity. Interestingly, this behavior resembles organic-inorganic hybrid perovskites, materials known for solar cells and adaptive electronics. The data fit the theoretical models well, strengthening the case for these mechanisms. Next, we'll see how this material performs biologically, starting with antimicrobial activity. With the complex successfully synthesized, the crucial next step was to evaluate its biological potential. The investigation focused on its antimicrobial properties, a critical field of research given the global rise of drug-resistant pathogens. The researchers employed the Agar well diffusion method, a standard technique where a substance's effectiveness is measured by the size of the zone of inhibition, a clear area where microbial growth is prevented. They tested the new copper complex against a diverse panel of 6 medically relevant microorganisms, comparing its performance directly against the uncomplex Schiff-based ligand. The results were immediately striking. Against the gram-positive bacterium Bacillus subtilis, the copper complex produced a large 30mm inhibition zone, a remarkable efficacy that placed it very close to the performance of ampicillin, a widely used antibiotic standard. The complex's power wasn't limited to bacteria. When tested against the opportunistic fungal pathogen Candida albicans, it created an impressive 20mm zone, an activity level comparable to the potent antifungal standard, amphotericin B. This trend of superior performance held true across the entire panel. In every case, the copper complex consistently and significantly outperformed the free ligand. So why does adding copper make such a profound difference? The answer lies in Tweedy's chelation theory. When the ligand chelates or envelops the central copper ion, it neutralizes the molecule's overall charge. This reduces polarity and makes the complex more lipophilic, or fat-soluble. Since microbial cell membranes are composed of a lipid bilayer, this increased lipophilicity is crucial. It allows the complex to more easily diffuse across this fatty barrier and enter the cell, a feat the more polar free ligand struggles to achieve. Once inside, the copper ion acts as the primary weapon. It can interfere with cellular enzymes, but more critically, it participates in redox cycling. This triggers a cascade of reactions that generate highly destructive reactive oxygen species, or ROS. These ROS are cellular assassins, indiscriminately attacking vital components like DNA and proteins, causing catastrophic damage that leads to cell death. Building on these impressive antimicrobial findings, the researchers expanded their investigation into oncology. They sought to determine if the complex's cell-killing capabilities could be harnessed to fight cancer. For this, they chose the MCF7 cell line, a widely studied and representative model for human breast cancer. The complex's cytotoxicity was evaluated using the MTT assay. This is a colorimetric method that measures a cell's metabolic health. Living cells contain enzymes that convert a yellow reagent into a purple product. The intensity of the purple color is therefore a direct measure of cell viability. Less purple means more cell death. The results are quantified by the IC50 value, the concentration of the compound required to inhibit the growth of 50% of the cancer cells. In this context, a lower IC50 value signifies a more potent anti-cancer agent. The data revealed the copper complex possessed an IC50 value of just 18.4 micrograms per milliliter. In contrast, the free ligand required a much higher concentration of 25.2. This clearly demonstrates that the copper complex is significantly more cytotoxic to breast cancer cells, mirroring the antimicrobial tests and underscoring the vital role of metal chelation in enhancing its therapeutic potential. To truly understand the potential of this new material, we begin with its fundamental architecture. Detailed textural analysis provides a window into its nanoscale world. The results revealed a crystallinity of 66.9%. This indicates a sophisticated blend of ordered crystalline regions, which provide structural stability, and disordered amorphous zones, which can enhance properties like solubility. The average particle size was measured to be just 33.7 nanometers, placing this material firmly in the realm of nanotechnology, where unique properties emerge. Furthermore, these nanoparticles aren't smooth spheres. They exhibit a heterogeneous pore distribution combined with high surface roughness. Imagine a microscopic sponge full of intricate channels and a vast, textured surface ready to interact with its environment. This complex structure gives rise to an astonishingly high surface area, over 72 square meters packed into a single gram of material. To put that in perspective, that's like unfolding the surface area of a large classroom and compressing it into a pinch of powder. This immense surface area is critically important. It dramatically enhances solubility, as there are far more points of contact for a solvent to interact with the material. For biomedical applications, this means a drug loaded into the material can dissolve more readily in bodily fluids. The porous network also enables a controlled drug release capability. Instead of a single burst, therapeutic molecules can be housed within the pores and released gradually over time, providing a sustained and stable dosage. Beyond its structure, the material's mechanical response is equally fascinating. Using ultrasonic measurements, we discovered it exhibits auxetic behavior. This is defined by a negative Poisson's ratio, a rare and counterintuitive property. When you stretch most materials like a rubber band, they become thinner in the middle. This material does the opposite. It expands laterally when stretched. This unusual characteristic stems from its internal, hinge-like geometry at the molecular level, which reorients under strain. These auxetic properties are incredibly valuable for flexible bioelectronic substrates. Devices that are worn on the body must adapt to constant movement, bending, twisting, and stretching, without losing function. A conventional sensor might crack or delaminate from the skin when stretched over a joint. An auxetic sensor, however, expands along with the skin, maintaining intimate contact and ensuring the integrity of its conductive pathways. This leads to more reliable and durable wearable technology. Taken together, these findings paint a picture of a truly multifunctional platform. This copper Schiff base complex is not just one thing, it's a synergistic combination of features. It is electrically adaptive and mechanically versatile due to its auxetic nature, and it is biologically active thanks to its porous structure and the inherent properties of its copper core. This synergy unlocks a range of exciting potential applications. One clear path is in next-generation wearable diagnostic devices. Imagine skin-like patches that conform perfectly to any part of the body, continuously monitoring vitals or biomarkers in sweat, even during vigorous activity. Another promising area is in implantable biosensors. These devices could be placed inside the body to monitor post-surgical healing, track disease progression by responding to temperature or electrical signals, and wirelessly transmit critical data to clinicians in real time. Finally, it could revolutionize wound healing platforms. An advanced dressing made from this material would not only conform perfectly to a wound, but also manage moisture through its porous structure. Crucially, The slow, controlled release of copper ions would provide powerful, sustained antimicrobial action, preventing infection and actively promoting a healthier healing environment.
As we come to the conclusion of this episode, I, Professor Dr. Salah Lotfy, from the Egyptian Atomic Energy Authority, would like to express my deepest gratitude and sincere appreciation to all the researchers who contributed their remarkable effort in producing this valuable scientific work. Special thanks go to Dr. Emad Mousa, Physics Department, Faculty of Science, Cairo University, Giza, Egypt. Dr. Ahmed Tammam, Physics Department, Faculty of Science, Cairo University, Giza, Egypt. Dr. Ahmed Refaat, Chemistry Department, Faculty of Science, Cairo University, Giza, Egypt. Professor Dr. Gehad Mohamed, Chemistry Department, Faculty of Science, Cairo University, Giza, Egypt, and Nanoscience Department, Basic and Applied Sciences Institute, Egypt, Japan University of Science and Technology, New Borg El Arab, Alexandria, Egypt. Their dedication and expertise have been instrumental in bringing forward research that bridges physics, chemistry, and nanoscience. And of course, I extend my heartfelt thanks to all of you, our viewers and supporters of For Science Salah Lotfy channel. I invite you to share your thoughts, questions, and reflections on this research in the comment section below. Your interaction not only enriches the scientific discussion but also helps us build a stronger community passionate about knowledge and discovery. Thank you for being with us. Stay curious, stay inspired, and until the next scientific journey, this is For Science Salah Lotfy channel.